developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
We are working on a semiconductor laser, and we're trying to take it from a technology readiness level 1 to 4. In particular, in the project, we're working on the semiconductor laser and we're trying to increase its brightness. Now, to increase the power in a semiconductor laser, the most straightforward thing is to just increase the active volume. The problem is you have more modes that come in, and so then you're essentially stealing your brightness. To do this, we're going to use what's known as a photonic crystal surface-emitting laser. These are devices which use a two-dimensional refractive index pattern, which basically creates an index profile which can engineer the modes of the cavity. And so what we want to do is come up with a structure which allows just one mode delays. This has been pursued for more than 20 years, and up till now, what people typically do in order to make these two-dimensional photonic crystals is they etch holes into a semiconductor, and then they epitaxially grow over that to seal off the holes. So this is potentially unreliable. So what we would like to do in this work is to replace those encapsulated voids with dielectric.
So one of the first processing milestones that we achieved was developing a standardized e-beam lithography process for the thin SiO2 photonic crystal patterns. Whenever we're drawing a new photonic crystal pattern, I will first deposit the SiO2 layer onto the sample and clean the sample along with the design that we would like to try for the first time. After giving that sample to him, he will draw several patches of the same pattern with varying e-beam current or doses. I'll then cut that sample into many pieces and perform the same dielectric etch with varying time points, and then determine which e-beam dose was the most effective for that design. We'll then keep track of those things with each design so that by the end of it we have a log of consistent, repeatable e-beam parameters that we need to set. Another one of the second month milestones that we achieved was the longitudinal mode overlap simulations. So we've been using the finite difference method mode solver just in Python to evaluate the modal overlaps for the active region and also for the photonic crystal region. So we input the refractive indices and the thickness of the layers, and that forms into a grid, and we solve for the eigenmodes and the modal effective indices for that desired wavelength. And then we can estimate the modal overlaps for various structures, for changing the photonic crystal layer thickness or position within the pixel structure, and then we can decide which photonic crystal thickness or position is optimal.
Now, normally we grow on perfectly crystalline, atomically smooth 3-5 wafer surfaces. So the challenge here lies in growing on top of patterned SiO2 photonic crystals. The SiO2 is amorphous, so it is critical to avoid deposition on those regions in order to prevent random polycrystalline growth. So the secret sauce lies in a process called selective growth, where the 3-5 material only deposits on the wafer surface and ultimately buries the low index photonic crystal in high index single crystal semiconductor material. This combination of patterning and epitaxial regrowth opens completely new ways to control optical modes in 3-5 lasers, and so we're excited to be part of this project.
I'm here in the semiconductor laser testing lab. One of the things we are very interested in is high brightness semiconductor laser sources at infrared wavelengths. The team at University of Illinois is proposing and working on a high brightness 1550 nanometer laser using indium phosphide and photonic crystal surface emitting lasers to reach these high brightnesses and high powers needed for applications such as LiDAR. And 1550 is good for eye safety, and it's also a telecommunications wavelength range. And the techniques they're using, we will be able to leverage for other programs for high brightness semiconductor laser sources.
So we accomplished several of our milestones in the first increment of this project. The first 2-month milestones that we achieved were the development of the electron beam lithography process for the thin SiO2, and also the development of the longitudinal mode simulations.
We were also able to achieve high fidelity dry etching of both indium phosphide and dielectric, as well as achieving selective overgrowth and lateral epitaxial overgrowth, both from indium phosphide and from a quaternary indium gallium arsenide phosphide, which to our knowledge is the first that's been achieved.
And in month 6, we were able to get done photo dumped edge pixel measurements, along with month 9 achievement of buried dielectric pixel, which are fabricated and characterized.